So we were evaluating more limits last night, and you, I'm assuming, hopefully, have already checked your answers. As I continue to mention, they're all in the back of the course pack with the solutions in most cases, so you've already seen not only the answers, but how most of these were worked out. I'm hoping that's why there weren't a huge number of questions yesterday. Like, be happy to go over some of these. You know, the first one, two, three of them all had something very much in common, which was they were factor problems, right? Um, we can't substitute directly, or we would get 1 minus 1 over 1 minus 1, and 0 over 0 is not something we can do. So let's do some algebra. Difference of squares and the denominator. Now we get rid of the issue in the bottom, which was the x minus 1. All we have left is 1 over x plus 1. Notice how I continue to write that limit. Now I'm going to plug the 1 in, though. That's called evaluating the limit. And that substitution step is basically what it is the point where you get to drop the limit. I can now get rid of the limit. Um, you don't want to write the limit for too long, or you'll lose notation points. You don't want to lose the limit too soon, or you'll lose notation points. So pretty much what you've seen here is what you need to do. Let's pretend all that stuff went away, and let's also pretend that you were more interested in this guy. Well, um, the top is a trinomial, so we'll factor into binomial. T minus 2, t minus 1. The bottom is perfect squares. T minus 2, t plus 2. Notice if I put a 2 in, I'll get 4 minus 6, which is negative 2 plus 2 is 0 over 4 minus 4, which is 0, 0 over 0. Now you're starting to see why we can't do these directly through substitution. Once we get rid of that t minus 2, though, good things happen. All I have left is the limit as t approaches 2 of t minus 1 over t plus 2. I can now do that evaluation step. I lose the limit notation at that point, and I get an answer of 1/4. That's it. That's your answer. Okay. That's how you do those. 23 is very similar. I think on 23 we would factor out an x squared. Once those x squareds go away, you can do your evaluation. I think on that one all you get left is 8 over negative 16 in the end. And what is that, negative 1/2? Yeah, negative 1/2. All right. 24 was a little different. 24 is that problem that I just know you guys aren't going to dig very much because a lot of you guys are not huge fans of fractions. And my recommendation is you isolate what the um, least common denominator is, or at least identify it. And it's going to be 2 plus x times 2. And although you could get common denominators up here and then add those together and then multiply by the reciprocal of x, I would get rid of those compound fractions immediately by multiplying by 2 plus x times 2, what we just said, the common denominator. When you do that, don't know why I put a fraction bar there. Good things happen on the top. 2 plus x cancels there, and I just get a 2 minus the 2 cancels here, and I just get a 2 plus x. Don't forget your parentheses, or you will be off by a sign. Okay. Nothing cancels on the bottom, and that is a common mistake. People forget all that good stuff down there. So on the top, the numerator, right? The numerator, all that's going to be left once the 2 minus 2 cancel out is a negative x. Now in the denominator, I still have a 2x times 2 plus x. But I'm not going to have this x for very long. Those x's are going to cancel. If you go back and watch the example we did yesterday, it's part of the extra examples that looked very much like this, except it was probably not a 2, it was probably another number. You're going to see something that looks just like that. Okay, so all I have left now is a negative 1 on top and a 2 times 2 plus x on the bottom. Remember, the original reason I couldn't do this is because you can't put a 0 in there. We just made that cancel. So that means we can now substitute our 0 and get our answer. And by the way, I think I did a graph of this one. Yep, there it is. And if you go to 0 right here, you can see that we're crossing right at about negative 1/4. And in fact, I can't find it with the calculator because it's actually an undefined value. Remember, it's 0 over 0. But if I use the tables on the calculator, it would near that value. And the graph certainly looks like it's close to that value. So that's a good deal. All right. Do we need to do the last one? Ooh, maybe. It may have been a while since you guys factored out a cubed binomial. I think the work is all in the course pack, but oh, what the heck? We'll just do it real quickly. So I know that if I square 2 plus x, I get 4 plus 4x plus x squared. But there's still another 2 plus x that has to be multiplied. So if you're really having a hard time keeping track of these, use the old box method you learned back in Algebra 1, where you put your trinomial across the top and your binomial here, and you multiply and then combine like terms. But if you're looking for a slightly less ambitious way of doing it, just keep track of what you got. You got one constant and only one constant, 8. We're going to have a couple x terms. We're going to have a 4x times 2, so 8x, and an x times 4, that's 4x. 8x and 4x is 12x. We're going to have a couple squared terms. We're going to have a 2 times x squared, so that's 2x squared, and a 4x times x, that's 4x squared. 2x squared, 4x squared is 6x squared. And we're only going to have one cube. We're going to have x squared times x, 1x cubed. Don't forget your minus 8, because we want it to cancel right now. We can now factor out an x, right? From 12x and 6x squared and x cubed, and get rid of it. And that's it. That's what was keeping us from doing the problem in the first place, was that pesky x in the denominator, and now it's gone. So we can now plug our 0 in and evaluate, 12 plus 6 times 0 plus 0 squared is 12. So those are the more algebraic problems that you had to do here. The next 5 were more trig type problems. This one was very similar to one we talked about, right? We're really looking for a sine kx over kx relationship. I'm missing a 2 down here to make that happen, but that means I'd also have to put a 2 up here. We better pull the top 2 out front because we don't really need it. And we know the limit of 2 is 2, no matter what we're approaching. then we have the sine kx over kx relationship. And remember, this thing is substitutable by 1. Not the limit of 1, just 1. And there you go. Done deal. It looks like I have an x in the denominator, and I'm going to go ahead and factor that out. And there's what I'm really looking for. It looks like it's going to be divided by the multiplication there, right? So the limit of sine x over x as x goes to 0 multiplied by the limit. And what's left? Not 2x minus 1, 1 over 2x minus 1. You got to pay attention to where that is. So this whole thing turns into a 1. This has to be evaluated. So I get 1 times 1 divided by negative 1 is negative 1. So negative 1 is our answer for number 27. Looks like 28 is going to be not separated by division, but rather separated by multiplication, or addition. So not separated by multiplication, but by addition. I'm going to split the fraction, is basically what I'm going to do. So limit as x goes to 0 of x over x plus the limit as x goes to 0 of sine x over x. So, x over x is just 1. This, by definition, by substitution, right? It's our identity, is 1. The limit of 1 is 1. 1 plus 1 is 2. Keep that limit until you evaluate. Just don't skip steps. That's the big thing. This guy might have been tricky because we didn't really look at 1 very much like that. But there's another way of writing sine squared, isn't there? Sine times sine. And I really only need 1 of those to go with my x. So let's split this limit by multiplication. Be careful with multiplication. We don't have common denominators. Otherwise, it would have been a sine x squared on the bottom. It's not. I only get the denominator 1 time with multiplication. This dude turns into a 1. This dude turns into a sine of 0. By the way, the sine of 0 is 0. Boom. 0 it is. I wonder why I'm writing crookedly. That's odd. I should probably talk to like some kind of a psychiatrist about that. And then this last one, probably the trickiest one, just because I have some things and I don't have other things. I mean, I really need a 4 on the bottom and I really need a 3 on the top, because if the limit of, sine 3x over 3 goes to 0, then the limit of 3 over 3x over sine 3x goes to 0. 1 is its own reciprocal. And so if I take the opposite of our normal sine, x over x, and flip it to get an x over sine x, 1 is 1. It should still go to 0. The only reason it works that way is because we are approaching 1. 1 is 1, and if 5 over 5 is 1 and you flip it, you still get 5 over 5. That's kind of why that works. I need some stuff here, though. I need some stuff. I need an x up here because, it has to be sine of 3x over x. But if I need an x on the top, I need an x on the bottom. But I also need a 4 on the bottom because I've got the 4x here. That means I need a 4 on the top. So what I really am going to have here is 4 times 3x times sine of 4x over 4x times the sine of 3x. So now we can play favorites, right? We're going to hook these two dudes up. We're going to hook these two dudes up. This guy's just going to float out front because he's a constant that doesn't fit with anything. sine 4x over 4x is the orientation we're used to. The 3x over sine 3x is the reciprocal of what we're used to, but remember, because it's got a value of 1, it's still going to approach 1. It's probably just going to approach it from the opposite direction. So 4 times 1 times 1, of course, is 4. And there you go. Just like the work you saw in your course back, except with thrilling verbal play-by-play. Probably not the neatest handwriting in the world, but what can you do, right? 31 and 32 were these kind of true-false questions. So we just had to look at the graph and see what was happening. Like, what's happening as I approach -1 from the right. I think, well, it looks like the left, but I see a little thing going up and down. Looks like the height of the graph is approaching 1. So it looks like that's right. I am approaching 1. That's probably true. What about approaching 0, right, from the left? So approaching 0 from the left. Well, the height of this graph is approaching the height of 0 as x approaches 0. So once again, that looks like it's true. Okay. What about C, approaching 0 from the left? Well, we just did C. We just approached 0 from the left. We're approaching a height of 0. Now, the function's value at x equals 0, f of 0, looks like it's 1. But that's not what limits care about, remember? Limits care about what you're approaching, not what you're equal to at that value. Are the left and right limits equal as we approach 0? Well, the left limit we already said was a height of 0. The right limit we haven't looked at. If this graph, if the x's move towards 0, this graph is also moving towards 0. Yeah, absolutely. Those agree with each other. And because those agree with each other, the two-sided limit not only exists, but has to be equal to the limit of the one-sided limits. And so that makes all of those true. What is the limit as we, oh, this says the limit as we approach 0 is 1. Well, no. If I took off, this part right here, if I got rid of the limit part, then that would absolutely be a true statement. But f of 0, I guess I'd have to plug the 0 in. F of 0 is equal to 1. We see that right up here. But that's not what it's asking. It's asking what height are we approaching from the left and the right. And it's the height of 0, not 1. The limit is, the limit as we approach 1 is equal to 1, is it? I don't think so. Because as I approach 1 from the right, the height is 0, and as I approach 1 from the left, I'm approaching a height of 1. And so 1 is not equal to 0. In fact, you could say the left limit was 1 and the right limit was 0, but you couldn't say the overall limit was 1 or 0. The overall limit does not exist because the two-sided limits don't agree. What's happening as we approach 2 from the left, right? 2 from the left. Well, we're approaching a height of 0. Maybe they thought you'd say, oh, look, I'm approaching 2. Well, yeah, they say the x's are approaching 2, right? What are the y's approaching? The limit is a height, true? So false for that one, false. And that's how you do problems like that. If you would also like me to walk you through 32, let me know. Come tomorrow to help session, and I'd be happy to go through it. But it's really the same idea. Do the one and two-sided limits exist or agree? So, as we approach 0, as we approach 0, the left limit is approaching the height of 0. The right limit is approaching a height of 0. So I would say the limit exists there. But as we're approaching 1 from the right, the height we approach is 1. And from the left, the height we approach is 2. So we have a different one-sided limit, so the limit does not exist at 2. As we approach 2 from the left, we're approaching a height of 1, right? As we approach 2 from the right, we're approaching a height of 1. So even though there's a hole there, a removable discontinuity, and the actual value of f of 2 is equal to 2, it is definitely still a limit. A limit exists there as we approach 2. I don't know if that was an answer. Well, here it says the limit as we approach 2 does not exist. That's totally false, right? Because we just said it did. This is an interesting one. For every value between -1 and 1, so that's from -1 to 1, for every value in that interval, the limit exists. So there can't be any jump discontinuities or infinite discontinuities, and I don't see any. So I would have to say that that is probably good. It's probably true. But if you have any more questions on these, they are very common types of questions you'll see on both like my quizzes and tests, but also on like AP quizzes and tests. Please feel free to address it later. Here's the answers, 33 up through 44. Once again, you already have them in your book, so we don't really need them, do we? 33 and 33 through 36 were some matching questions. And this was kind of about factoring the top and figuring out, do we have a hole or do we have vertical asymptote, and what are things approaching? Because we know those holes are still going to have limits that exist. And so that's how that works out. Once again, if you want to go through any of those and really talk about them, we can. But which ones have removable discontinuities, which ones have infinite discontinuities because they're vertical asymptotes, and which ones, match up with that appropriate tables. I mean, the one thing that I see right away is only one of these is defined at 1. This table A, is 0. The rest all have errors. Well, that's because you can't divide by 0, right? So A would have to fit with 36, because that's the only one that if you plug in a 1, you don't get a 0 in the denominator. So, those are the kinds of things you need to look for. 37 through 42. So the first 1, 2, 3, 4 of these were greatest integer functions, right? Greatest integer functions, that stair-step function we studied back in Unit 1. So what is the limit as we approach 0 from the little plus, right? So from the right. So 37 says let's approach 0, x equals 0 from the right. And it looks like I'm approaching a height of 0. So this would be 0. But what happens if I approach 0 from, see the little negative, right? From the left. Well, the function is not at 0, it's down here. It's at a height of 1. And so that's going to be 1. And so, of course, the two-sided limit is not going to exist for this graph at 0, or any integer, because at every integer we have a jump discontinuity. And so because of that, you have infinitely many jump discontinuities. You're never going to have limits that exist, two-sided limits that exist, right, at integer values. So I think that was a big part of what they wanted you to get out of this problem. What about 39? And well, 39 is approaching 0.01. So it's approaching something that's really, really close to really close to 0, but just on the side, and it has to be approaching it from both sides, because I don't see a little plus or minus. It's a two-sided limit. So the answer is definitely going to be a 0 there because that's where all the values are between 0 and 1. Okay. The last greatest integer function was what happens as we approach 2 from the left. So here's 2. We're approaching from the left with the red arrow, from the right with the blue arrow. As I approach 2 from the left, my height is 1. As I approach 2 from the right, my height is 2. They wanted it from the left, so the answer for number 40 is 1. Okay. 41 and 42, we switched functions. This is actually the same function I think we looked at number 19 yesterday. Number 19 yesterday. And when you divide a number by itself, you get 1, which is what happens if you have a positive into this, because the absolute value of a positive is itself, and so a number divided by itself is 1. However, if we're over here instead, negative numbers, right? The top stays negative, but the bottom turns positive, and I'm dividing a negative by a positive, and so I get a negative 1 instead. And of course, at 0, we can't have any values because 0 divided by 0 is undefined, technically indeterminate. So what's the left limit here for number 41? Well, it's a height of 1. So the limit is 1. But I think you'll agree that as we approach 0 from the left side, I'm approaching a height. I'm at a height and approaching a height of negative 1. So the limit there is negative 1. So that's up to 42. 43 and 44 really just wanted you to apply the properties of limits. These are the only ones where you really have to be careful with your constants and that kind of thing. So, normally these kinds of problems you're not going to see as far as, problems you have to show work on, maybe a multiple choice question or something like that. But if you did have to show work showing the properties of limits, like on A, you'd have to use the limit properties and split the limit by addition in this case, right? And then the limit of a constant is itself, no matter what you approach, and then by substitution, this is 0, and so you get 0 plus 3 is 3. So you'd split this one by multiplication, limit of x, so we approach 4 times limit of f of x, so we approach 4 the limit of x as we approach 4, well, it was going to be 4, right? It's the identity function. And then the limit of f of x again was 0. So this time 4 times 0 is 0. So that's kind of how you do these. And I think I have them worked out pretty fully in your solutions manual. But once again, if you want to see any of these really fully worked out, let me know. All right, 45 is asking you to first sketch the graph. So I just kind of sketched these lines here. And then it wasn't that big a deal. This starts at 3 and then goes down 1 over 1. It only went over 2 points before the other function took over on this piecewise, but that's pretty much what you get there. The other one started at 1 and went up 1 over 2 at a slope of 1/2. So it didn't start at 1, but it started, if I plug a 2 in there, 2 over 2 is 1 plus 1 is 2. So this is how this graph looked. Notice that we definitely get a jump discontinuity at the break point of this graph at 2. Okay, that's totally not what's supposed to happen. It was supposed to be a square, not a circle. I thought I drew a square. There we go. So you can see what's happening there. So what that means, as far as the left and right limit goes, is they're going to be different. One of them is going to be approaching 1, and one of them is going to be approaching 2. Let's break that down. The right limit, so they wanted us to put a 2 in, right? The right limit of f of x, so coming from the right towards 2, is approaching a height of 2. But the left limit, as we take f of x and approach 2, is approaching a height of 1, right? And so does the limit exist at 2? And the answer for this problem would be no, it doesn't, because the right limit and the left limit don't agree. They are not equal to each other. The limit, which is also known as the two-sided limit, only exists if the one-sided limit is the same. Now, 46 was almost the same problem, except at 2, whereas this one was undefined, they did define the value as 2. And secondly, whereas this function was x over 2 plus 1, this one was just x over 2. And so 2 divided by 2 is just 1. And so this guy dropped down, right? It dropped down 1 unit. So we still have a discontinuity at 2. But notice this time, it's a removable discontinuity. It's a whole. And so that means that the left limit and the right limit will approach the same thing as we move into this guy from the left. We're approaching a height of 1. As we move into 2 from the right, we're also approaching a height of 1. So does the limit exist as we approach 2? Yes, it does, because the left limit and the right limit agree. Even though f of 2 itself is equal to 2, creating that removable discontinuity, that's okay. That's not what they were asking about. So 45, 46, very similar, just slightly different, but the small difference did make a difference, but the limit existed on 46. This one was kind of weird because you had like a rational function that was approaching its vertical asymptote on the left side, and so I kind of drew this guy going down. On the right side, it was a cubic, so I did plug a 1 in, and I got 1 minus 2 was negative 1 plus 4, 5 is 4. And so I started at a height of 4, and then it's going up like a cubic would. So this is kind of a mix between a jump discontinuity and an infinite discontinuity, but it's different. Like the right limit is just approaching a height of 4, but um, the left limit is approaching negative infinity, and so this is 4, and this is negative infinity. We're going to talk about limits in infinity next week, and infinity is not a real number, so infinity is not a limit. But for one-sided limits, you can use infinity and negative infinity to describe the limits. We'll talk about that next week. But these are definitely not the same value. So does the limit exist? No way, for so many different reasons on this problem. Okay, and then 48 was the last problem, and it was a parabola for the most part, right? It was 1 minus x squared, so it was reflected and then horizontally translated up 1, or vertically translated up 1. It just kind of looked like this, except it was not defined for some reason at negative 1. So if I go back to negative 1, there was a hole there, okay? At the same time, they wanted me to define the function at negative 1 with a value at 2. Okay, so that's kind of what it looks like. Does it really make a big difference on how we evaluate this? No, because it's a removable discontinuity. It's just a hole. So as we approach negative 1, right, from the left, we're approaching a height of 0. And as I approach negative 1 from the right, I'm approaching a height of 0. So the limit of f of x as x approaches negative 1 that was really sloppy, sorry, is equal to 0. The limit exists because the two one-sided limits exist. And that was a huge part of what so many of these problems we're trying to get you to understand is if the two one-sided limits agree, there is a two-sided limit. There is a limit. So hopefully you're starting to feel comfortable with that concept, and hopefully you're starting to feel comfortable with limits in general. Um, it's new, so I know that it's not easy, but there haven't been too many questions put to me yet. We're not going to learn anything new tomorrow, so please, I guess tomorrow doesn't make much sense if you're watching this on Thursday. This is Wednesday. It's almost tomorrow. It's like 11:30, so it's late Wednesday night. So on Thursday, we're not going to learn anything new. We're just going to review. I've got a bunch of problems in the course pack that I will post for you to work on, and you have all the solutions for those to look at. And so I'll go over selected problems in a video for you and stuff. If you're watching this tomorrow morning and you still have not submitted your homework 21 through 30, the worked out problems, it's late, so get it in sooner than later. The longer you wait, the less, the more partial credit you get. Um, and yeah, let me know how I can help you. Hope you're doing all right. And should be a brief limits quiz coming up on Friday. Bye.